And our final example is where we work out the electric field near a sheet of charge. This one paves the way to looking at parallel plate capacitors, which are very important because the straight sheets of charge are the ones that give us the uniform electric fields that we use in many applications. So we are imagining an infinitely large sheet of charge, and the surface charge density is sigma coulombs per square meter. Again, we've chosen a cylinder for our Gaussian surface, and the good thing is you can see from the side view that since all the electric field is going horizontally, that means only the ends of the cylinder will have electric field coming out through them. The whole curved surface of the cylinder has no electric field lines going through it at all, and so it won't contribute anything to the electric flux coming out from that cylinder. So we're going to draw our sheet of charge like this, and we're going to look at a surface, a Gaussian surface that is a cylinder. As usual, a cylinder is a nice easy surface. It's only got 3 surfaces that make it up. And so we have electric field will come out from each end of the cylinder because the electric field will be coming out from the line of charge. Now we're looking at surfaces that are a distance z away from the line of the sheet of charge, and we're looking at a little cylinder that has got a radius r, and our sheet of charge has a charge density of sigma coulombs per square meter. So for the curved face of the cylinder, there isn't going to be any electric field. So it won't be coming out because it is parallel to the curved face. So it's only coming out through the ends of the cylinder. So flux for the cylindrical curved face is going to be 0. Let's look at the ends of the cylinder. And we have that they each have an area that is pi r squared. And so if we look at the left-hand end of the cylinder here, then we can say that this is for the integral for the left hand of E times the area, and E is a constant, so we can take it out the front and we just have the integral of the area there, which is E times pi r squared, and the flux on the right, so that was the left, flux on the right is going to be the same because the electric field is coming out both sides, it's symmetric, and so we also have that is the integral of the right, E dA and E dA there, so we will also have E pi r squared. So now we have that the E naught times the whole integral of E dA is the enclosed charge. And so now we've added what this is. We have E naught times the flux out of the left plus the flux out of the right, and there's nothing out of the curved face, and that is the enclosed charge, which is going to be sigma times pi r squared, because we're only looking at the little bit of that sheet of charge that is inside the cylinder. And so we end up with, and I think we'll have to go over the page for this. So continuing on now, we have E naught times the only parts of the surface that had flux through them, and that equals sigma pi r squared. So we've got E naught times E pi r squared plus E pi r squared for the other end, pi r squared, and that is sigma pi r squared. And you notice that I can simply cross out the pi r squareds, and I'm left with 2 times E naught times E equals sigma. And so the electric field is just sigma over 2 E naught, which is quite a simple result.